Okay, so I'm going to give you the general ideas behind diffusion controlled reaction and activation controlled reactions. Realizing that these are generalizations, and as you get closer and closer to specifics of your reactions, different nuances are going to shine through. Okay, so if we have, and this is happening in solution, so if we have a solvent of some sort, and we have our A and we have our B, and this is in our solvent, and so this is still A plus B yields products. I'm going to switch to a marker that you can read. Okay, so the frequency of A and B finding each other is actually quite low. Unlike with a gas phase where it was like 10 to the 34, I think was the collision density. For A and B to find each other, it's actually quite challenging unless you have just pure A or pure B. And so compared to gas phase, finding each other is very low. The other thing to think about is there are solvent effects. And so the intermolecular interactions of just A might be, so there's another A right here. So it might be A and A interacting with each other, A and solvent interacting with each other, and A and B interacting with each other. So you have multiple types of intermolecular forces that are going to be dictating A's interaction with all of the different possibilities. Okay, so the interaction also depends on what are called cage effects. And so this would be, so if you have, say, a cation, there are going to be molecules that are going to orient themselves such that this is a partial negative, oops, negative, and then your partial positives are all on the outside. And so here, you're going to have what are called separation effects. So if this is the solvent, and an example would be sodium chloride, and so, oops, I got those backwards, my bad. So here's water. So so this would be HOH, and so this is an overall positive. This is the overall negative. So you're going to have the solvent molecules orient themselves such that their negative dipole is coordinating with the positive sodium. Well, this area on the outside is going to be a cage, or cause a cage effect. And so you're going to have a different type of interaction. So if there's a B or molecule here and A is right here, now there's this solvent separation between the two. And remember, the kinetics depends on the cross section. So if there's some sort of area here and an area here that these need to get close enough such that they can interact with each other, the solvent effect might dictate how likely that is to occur. Okay. So for A plus B yields products, we have a rate constant times the concentration of A times the concentration of B. So A plus B yields P. You can have, so here's our along a reaction coordinate. You have A and B separated, your products, but then there has to be some sort of transition state where A and B become an activated complex such that A and B are still unique to each other, but they're in the right orientation such that they can then react to become the products. And so you can really break this up into A plus B is in equilibrium with AB, and then AB can go to the product side. Go team. But this is going to be in solution. So depending on which liquid is present might dictate if this is going to actually form or not. Because if A and B are separated by some solvent that won't let them migrate, that is going to cause an impedance to this reaction moving forward. So I'm going to call this KD. KD prime is the reverse reaction, and then KA is the forward reaction from the AB complex. Okay, so if I want to then look at the rate of the intermediate AB, so the rate that AB is formed is equal to plus KD times concentration A, concentration of B, minus KD prime, concentration of AB, minus KA, concentration of AB. Oops, that should be a K. Okay, So all of these, based off the steady state approximation, which we can apply here, this will all equal 0. So d, whoops, so dAB dt is approximately equal to 0. This is steady state approximation. Yay, we just learned that. And then this results this reduces then to AB is equal to KD times A times B divided by KA plus KD prime. And we know that, horrible use of board space, we know that dP dt, make this concentration P, is equal to Ka concentration of AB. So then I can just plug this in to this, and that gives me Ka times Kd concentration of A concentration of B divided by Ka plus Kd prime. Cool. So this is the rate of our product formation right here. Okay, sorry about the poor use of board space. Deal with it. So we've got Ka, Kd times AB, and then again, these are the two quantities that have to find each other in solution. So based on the steady state approximation, now we can start to ask that question, well, which one is going to dictate the reaction? And this is where the difference between diffusion controlled and activation controlled comes in. So for diffusion controlled, if Kd prime, this value, is much, much less than Ka, what this means is we've got A plus B, Kd, Kd prime, AB, and AB goes to products for Ka. If Kd prime is much, much less than Ka, so the rate that this goes back to A and B, if that's the case, as soon as this is formed, it essentially goes to products, is what that's saying, which means that VR reduces to, so if this is really small, this reduces to Ka, Kd, quantity A, quantity B, divided by Ka, those cancel, and I'm left with just the rate of reaction depending on this forward reaction. Because as soon as AB is made, you've got a reaction and it's going to go to products. What that says is if you got A plus B, AB is the activated complex, and then products happens, then if you're in solution, all right, so you're in solution and A and B find each other, they diffuse towards each other. As soon as they diffuse and find each other, you've got a reaction occurring. This is called diffusion controlled, okay? Diffusion controlled. Cool, diffusion controlled. But if we have, however, instead of Kd prime is much, much less than Ka, let's take the other extreme. If Kd prime is much, much greater than Ka, such that as soon as A and B are formed, they immediately go back to A and B such that P is never formed, even if A and B find each other. So they diffuse around and they find each other, and then it still doesn't necessarily yield a product. This then becomes, so if Kd is much, much greater, this becomes Ka, Kd, A concentration of B divided by Kd prime, such that A and B can find each other in solution, but still no products. This is called activation controlled. And what that's saying is there's still not enough energy of activation associated with this AB complex in order to get it to yield a product. So A and B can touch each other, they can find each other in the solvent, but they can't actually yield a product. So let's see, what else do I have to say? So the rate depends on the equilibrium. Oh, so in this case, the rate depends on the equilibrium between A plus B and AB. And where does equilibrium lie? If equilibrium lies way over here, such that you have a high concentration of A and B, now it's just a probability game of if you have a lot of numbers of AB out there, odds are some of them are going to convert to P. If you have very few, if equilibrium lies way over here, such that AB never forms, or AB rarely forms, such that of that rarely forming, only a few of them are going to then convert into P, well, then your reaction is even more restricted from going forward. Okay, cool. That's diffusion controlled.